Hey everyone, and welcome to this explainer. Today, we are embarking on a really incredible vertical journey. I mean, have you ever actually stopped to consider the sheer scale of the engineering required to extract oil and gas from the crushing depths of the ocean? We are talking about absolutely extreme environments here. Immense pressures, freezing temperatures, the whole shebang. So in this explainer, we're going to unpack the fascinating world of offshore facilities, flow assurance, and well integrity. We'll be drawing directly from our source material to show you exactly how this massive undertaking actually happens.
Really think about it for a second. How do you control immense pressure at the bottom of the ocean? We're dealing with these chaotic, high-pressure forces deep underground that naturally just want to burst straight upward. Taming those forces? Well, that requires an absolute masterclass in modern engineering. Every single step of the process has to be calculated flawlessly to prevent a total disaster.
So, to wrap our heads around this, we're going to break the journey down into four main stages. First, securing the well. Second, keeping the oil flowing. Third, structures of the sea. And finally, fourth, handling the excess gas. Let's get started.
All right, let's dive into this. Literally. We're starting deep underwater with Section 1, securing the well, which is exactly where extraction begins. You know, if there's one foundational rule to offshore drilling, it's what the source refers to as the two-barrier philosophy. Basically, this involves applying technical, operational, and organizational solutions to prevent any uncontrolled release of fluids. Conceptually, it's kind of like a medieval castle's defensive design. You wouldn't just have one single solitary wall protecting your keep, right? You'd have multiple, overlapping layers of defense to make absolutely sure nothing ever breaches your stronghold.
So what exactly are these modern-day castle walls? Well, your inner keep, the primary barrier envelope, is in direct contact with the volatile fluids. This includes the production tubing, the downhole production packer, and the subsurface safety valve. But if that inner keep is somehow compromised, you desperately need those outer walls. That's your secondary barrier envelope. It acts as your crucial backup containment, consisting of the production casing, the cement sheath, the wellhead, and what engineers actually call the Christmas tree valves. The big takeaway here is that redundancy isn't just an afterthought, it is built right into the very DNA of the well.
But even with all of those incredible barriers in place, there's a silent threat that engineers have to constantly monitor. The source material highlights the acute danger of something called sustained casing pressure, or SCP. Basically, this is a continuous buildup of pressure in the annular space, which is just the gap between the different casing pipes. If this buildup isn't carefully diagnosed and managed, it can literally rupture those heavy steel walls, leading to a catastrophic casing failure. It is just a constant, high-stakes battle of physics deep beneath the seabed.
Okay, so we've got the well safely secured, and the fluids are moving upward. But as that oil travels up from the deep earth toward the ocean floor, it hits freezing ocean temperatures. This introduces a major new hurdle. That brings us to Section 2, keeping the oil flowing and beating the cold. Here's the thing. Crude oil isn't just some simple liquid. It actually contains heavy alkane paraffin waxes. When the temperature of that crude oil drops below its wax appearance temperature, which is also known as the cloud point, those waxes begin to precipitate. Essentially, the cold, deep-sea environment turns the flowing liquid into a sticky, waxy mess, and that mess adheres directly to the tubing and pipeline walls, threatening to just completely choke the entire system. So how do engineers actually fix this? Well, to tackle this flow assurance problem, they use a brilliantly distinct three-pronged attack. First up is mechanical removal. This means physically scraping the wax out using wireline scratchers, cutting tools, or even sending a device called a pig right through the pipeline to clear it out. Second, we have thermal treatments, which is exactly what it sounds like, melting the wax away by circulating hot oil or hot water. And third, chemical treatments. This involves injecting dispersants, crystal modifiers, or aromatic solvents like toluene and xylene to just break down the buildup at a molecular level.
All right, now that we've kept the oil flowing, let's follow it all the way up. We are finally breaking the ocean's surface to explore the structures that actually process all this oil. Welcome to Section 3, Structures of the Sea, featuring these massive floating cities.
It is amazing how engineering innovation maps so perfectly to ocean depth here. In shallow waters, up to about 500 feet or so, rigid steel fixed jackets work perfectly fine, anchored right to the seabed. But as you go deeper into the 1,000 to 2,000 foot range, rigid steel would literally just snap under the sheer force of the ocean. So, engineers developed compliant towers. These actually flex and sway right along with the waves.
And if you're going even deeper, well, then we switch to floaters. The tension leg platform, or TLP, and the Spar use buoyant hulls and heavy ballast to float, all while being tethered super securely to the seabed. Finally, for the most remote deep-sea locations that are far away from any pipeline infrastructure, they use FPSOs. These are massive converted ships that process, store, and offload crude right there on the open ocean.
So from the deep wellbore, through the freezing pipes, to the massive platforms floating on the surface, our journey has one final stop. Welcome to Section 4, handling the excess gas. Let's look up to the sky.
When you're dealing with oil extraction, excess gas is just an inevitable byproduct. And here we hit a really fascinating, kind of counterintuitive truth. Naturally, you'd assume that setting something on fire on an oil rig is the dangerous option, right? But consider the reality here. Venting is the direct, unburned release of methane gas straight into the atmosphere. Because methane is so highly volatile, venting creates a severe, highly unpredictable explosion hazard right around the platform. Flaring, on the other hand, is controlled thermal combustion. By actually burning the excess hydrocarbons, engineers safely convert them into carbon dioxide and water vapor. So ironically, having an open flame up there actually mitigates the immediate fire risk on the rig.
But what's really fascinating here is the environmental reality behind that decision to flare. Beyond just the safety risks on the platform itself, venting invisible, unburned methane has a massive, massive impact on the climate. To put it in perspective, methane's global warming potential is, get this, over 28 times higher than that of carbon dioxide. So flaring isn't just about preventing immediate explosions for the crew. It's a calculated decision, driven by the absolute necessity to avoid releasing a significantly more potent greenhouse gas directly into our atmosphere.
Which brings us to one ultimate, pretty provocative question. As we've seen on this incredible journey from the seabed to the sky, extracting energy is a staggering technical achievement. It requires brilliantly overcoming immense pressure, freezing temperatures, and violent ocean currents. But how do we continue to balance these undeniable engineering marvels and our global energy demands with the delicate long-term impact on our planet? It's a hugely complex, multifaceted challenge that sits right at the intersection of human innovation, safety, and environmental stewardship. Thank you so much for joining me to explore this source material in today's explainer. I really hope this structured dive into offshore extraction sparked your curiosity and left you eager to learn even more about the incredible hidden systems that power our modern world.